Hello everyone and welcome back to my channel. Today we're going to be solving some physics problems from Electrodynamics by Griffiths. And so let's get right into it. So these problems are from chapter 2. This is actually the first problem from chapter 2. And if this is an interesting thing, then maybe I'll continue with some more problems from chapter 2. But yeah, this is problem 2.1. This is fairly simple, but I'm just going to go through the law which is behind this first, and then we can get into the problem itself. So this is the expression for force between two charges. So the two charges are small q and capital Q, and R is a vector. So if this is the position, if this is Q and this is capital Q, then capital Q is located at R prime and small q is located at R. So we get R is equal to, well, they're all called R. So cursive R is equal to R prime minus R. And of course, then we can get expressions for R square and R hat, where R hat is just the unit vector in the R direction. So with that out of the way, I think we can begin with the problem. Okay, so problem 2.1 is 12 equal charges Q are situated at the corners of a regular 12-sided polygon. What is the net force on a test charge Q at the center? And they've said that it's like each numeral on a clock face. So this is fairly simple because what we can do is we can form 6 pairs, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so by forming these, what we've done is that we've created that regular polygon-esque shape. And now we can put our test charge in the center. So this is capital Q and those are all small q. And we get two forces. I mean, we get 6 pairs of forces actually, but I'm only going to draw one of them. And so what you find is that this force is going to cancel out with this force. And your net force is going to be 0. So, I mean, you can do that for all the pairs, right? Because they're exactly opposite, so these are going to cancel out. And so that first part is fairly simple. Now, if one of the q's is removed, what would be the force on q? Now, they don't actually expect us to derive an actual value for this because we don't have values, but we can simply rewrite the force. So for example, say this charge is removed, then this force is gone, and so then this force is unbalanced, and so we can write this force as simply being this expression over here. So it's just 1 by 4 pi epsilon naught. Epsilon naught is the permittivity of free space. It's just a constant. And that's our expression. So that's all there is to part B. Now, say we have 13 equal charges Q placed at the corners of a regular 12-sided polygon. Now, what would the force on the test charge Q be here? Now, perhaps you're going to think it's 0 again, and you'd be right, but we need to, perhaps you're not sure. Like, I wasn't sure when I first did this. And so I did a more mathematically rigorous but slightly convoluted proof, which I'm going to show to you right now, okay? So what I'm going to show you is us taking the forces from all the individual charges. So say we have our test charge again, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's supposed to be a circle. Please ignore the terrible drawing. And so if we write this as 1, 0, because the distance really doesn't matter when we're trying to, well, just trying to prove that it's 0 for now. So say, just take it as 1, 0. And of course you could write it as k, 0 if you want, but it's really going to complicate stuff unnecessarily for now. Now let's take this point here, right? We have no idea what the coordinates for this point would be, but we can find out actually. So we know these points would lie on a circle, right? And if we took this angle theta, since it is a regular 13-sided polygon, this angle theta should be 2 pi by 13 in radians, because it's 1/13 of the whole circle. So we can actually get the x coordinate and the y coordinate for this from there. We would get the x coordinate as simply cosine of 2 pi by 13. And again, if this was k comma 0, then it would be k cos 2 pi by 13, which would be a bit of an unnecessary hassle, which is why we're just ignoring it for now. And this would be just sine of 2 pi by 13. And then what you notice that if we took this point, that's 2 theta. So you'd get x2 is equal to cos of 2 times 2 pi by 13, and y2 as sine of 2 times 2 pi by 13. And in fact, we could write any pair, any xi as cos of 2 pi I by 13, and any y as sine of 2 pi I by 13. Now, the reason this is relevant is that we want to sum the forces, right? So we know that the total F is going to be the sum of all the individual forces, right? And so if we now sum these positions, because we know that, okay, so we know that R is equal to R prime minus R. And so if we take the origin as R, then we actually just get R as the vector R as R prime. And so we can just think of this as being, well, if we take this as the position vector, then we can just say that the direction of the force is just going to be the sum of the directions of all the individual vectors. And so let's go ahead and do that. So we'll take this, and we get cos of 2 pi I by 13, and we'll just say x hat, which is the unit vector in the x direction. If you're used to I hat and j hat notation, then x hat is equal to I hat, and y hat is equal to j hat. Okay, and sine of 2 pi I by 13 y hat. And if you go ahead and calculate this, it's not very hard. You can plug it into a GDC, or if you don't have that, Desmos, then you get 0 x hat plus 0 y hat, or just 0, well, it's not newtons, but 0. And so what this means is that there is no force, because all of the forces cancel out. Now, this probably isn't as intuitive as this scenario, where we could just see, visually these two cancel out, right? But it's clear that here they don't. Now, part D is quite interesting, because it turns out that once again the answer is this, because actually if you think about it, it makes sense, right? Because here we know that F net, or actually I'm just going to write F total to maintain consistency, is 0 newtons, right? And so if we remove one of the charges, then the force is going to be the force of that one of the charges was exerting, right? Because if it wasn't, if that charge is removed, then the charge is no longer exerting that force, and so it makes sense that that is going to be equal to the force. And so actually it just ends up being the same thing again, right? So if you understood that reasoning, if you didn't understand that reasoning, I'm going to go through it again. So okay, you can imagine it as, say we are removing the 13th charge, and this is all the charges except 13. Okay, so this is equal to 0 newtons, right? So the charge of the 13th one is just going to be, well, technically it's going to be minus, but because we're not particularly dealing with directions right now, it doesn't really matter. So again, the magnitude of this is just going to be equal to this, and actually that's just going to come out to 1 by 4 pi epsilon naught times q by r square r hat, where r hat is of course the direction of that 13th charge, whichever one we want it to be. It doesn't really matter because we can move any charge. So that's all for this video. If you have any comments or suggestions or questions, please leave a comment, and if you enjoyed the video, please let me know, because then I'll be doing more of these Griffiths electrodynamics ones.